Some of the most extreme environments on our planet are the North and South poles, and these icy areas are changing all the time. And it turns out that these changes can have huge impacts on a global scale. Mapping these areas can give us better insights into the changes. But how do we map an area of Earth that is so hostile and so hard to get to? Find out next on Real World. NASA studies 6 unique spheres that make up our complex Earth system: the geosphere, the hydrosphere, the atmosphere, the anthrosphere, the biosphere, and the cryosphere. Earth's cryosphere includes all of the icy parts of Earth: snow, sea ice, lake ice, glaciers, permafrost, ice caps, and ice sheets. Understanding Earth's cryosphere offers insight into the past, present, and future behavior of Earth as a whole.
When we talk about the polar regions, we mostly talk about 2 types of ice. One is the frozen ocean sea ice, and it's just saline water that freezes. And then we have the ice sheets, which is ice on top of land, which is the ice mass of Greenland on top of Greenland and the ice mass in Antarctica.
The 2 ice sheets on Earth today cover most of Greenland and Antarctica, and together they contain more than 99% of the freshwater ice on Earth. NASA has been keeping a close eye on these giant ice features to better understand how they change over time and just how these changes impact Earth.
The ICESat mission was really a benchmark. It flew from 2003 to 2009 and gave us fantastic data during that time period. And over time, we were able to build up maps of the shape of the ice sheets, the thickness of sea ice, and the height of forests all over the world.
ICESat helped us document how ice was changing over the years, but new information raised new questions. So NASA is working on the next generation ice observing satellite, ICESat-2. And this satellite has a few more bells and whistles than its predecessor.
ICESat-1 was a laser altimeter in space, and it would send out a pulse of light 40 times a second and time very precisely how long that light took to go from the satellite, bounce off the surface of the Earth, and back up to the satellite again. It's the same idea behind radar detectors that measure how fast is your car going or how fast is a baseball thrown.
And for ICESat-2, instead, we have a much lower power laser, so think of it as a less powerful laser pointer. That single laser generates 6 beams that come down to the Earth, which allows us to sort of develop a profile of the elevations as we fly along. So we get a wider area than we did with the single beam on ICESat.
Sounds like a tough job. We know that measuring changes in elevation requires repeated, very accurate measurements over time, but achieving that kind of precision is not an easy task. Try using a stopwatch to time how quickly light reaches you when someone flips on a light switch. How quickly can you start and stop the watch? You might be able to get a few hundredths of a second, but the measures needed for ICESat-2 need to be much more precise than that.
Light, as we know, moves very quickly. In terms of actual time, it's just a few milliseconds or a few thousandths of a second between when the light pulse leaves and when it comes back again.
For ICESat-2, since it sends a laser down to Earth and then back up and then times that pulse to figure out what the distance is, it's really important that those 2 paths, the one that goes down and the one that comes back up, remain parallel to each other.
And so that the laser will bounce off the Earth and come back into the telescope, we have to keep them pointed at the same spot on the Earth. And so we have this onboard system that will move the laser around to follow the telescope as the telescope looks at different places on the Earth.
Scientists will be able to use the data collected to make precise topographic maps of Earth's surface, including the thickness of polar ice, height of vegetation, even the elevation of a glacial ice sheet, and to an amazing precision of about 3 centimeters. But how will all that information help us understand more about Earth?
So we go out to the community of users. We go and we talk to scientists at universities and federal and government facilities. We also talk to commercial users, and we talk to people that would generally use this information on the ground. It's not intended to be solely research. We really want to make the connection between the scientist and the society.
We think we know what people may be interested in, what type of data, but very often scientists are very smart people. They extract information from those data that we would never have imagined.
See, I don't think you will ever really know all the science for anything. That's what science is about. It's about new discoveries and new approaches and always finding new questions to ask and new people to apply the science to.
Zooming along at over 7,000 meters per second, 24 hours a day, 365 days a year, ICESat-2 can get a cool perspective of Earth's cryosphere. And these worldwide measurements will have lots of real-world applications. Thanks for watching. See you next time on Real World.